All right, our next topic deals with salts. Now, you've heard the word salt, and I'm sure most of you think that salt is sodium chloride, which is true a little bit. Sodium chloride is a kind of salt. It is called table salt, but it's not the only salt. In fact, there are thousands of salts. Salts are the creation of an acid-base reaction. In this case here, we have hydrochloric acid, which is HCl aqueous, and that is a strong acid. We'll revisit that in just a little bit. Sodium hydroxide is a base. In fact, that's a strong base. We're going to go through a double displacement reaction here, looking at the charges. Hydrogen is +1, chloride is -1, sodium is a group 1 metal, so that's +1, and hydroxide is a polyatomic ion with a charge of -1. And as we know, the sodium and the hydrogen are going to switch places in a double displacement reaction. So that's going to give us NaCl, which is your table salt, and that is going to be dissolved in the water in the system, which we have in the aqueous to begin with. And we know it's soluble because for two reasons. One, we put salt in water when we cook, we see it dissolves. The other is the fact that sodium is a group 1 metal, and group 1 metal ions, or ionic compounds, tend to be extremely soluble. Plus, the other one is hydrogen now with hydroxide, which we can write as HOH, but no one really writes it that way, although technically that's how you should think of it as a chemist. As the farther along you go into chemistry, hopefully in the next year, some of you, this is water, H2O, 2 hydrogens plus an oxygen. But it's technically hydrogen hydroxide because hydrogen hydroxide has been known to split, and that's what creates the acids. It creates hydrogen ions and hydroxide ions. But anyway, we can get true hydrogen and oxygen out of it if we use a process called electrolysis, but under normal laboratory conditions that is never going to happen. We're just going to get hydrogen hydroxide ions coming off. Now, so this is a strong acid. How do we know it's a strong acid? I gave you a list of strong acids, so let's revisit those real quick. Hydrochloric acid, hydrobromic acid, hydriodic acid, nitric acid, sulfuric acid, and then we got perchloric acid, and then we have chloric acid, although some people tend to believe that chloric acid really isn't by definition strong, and we'll talk about that pretty soon, but strong acids generally break apart when they are dissolved in water. They break apart completely, where most acids and bases do not do that. These 7 do. So anytime you see this, you know that this is a strong acid, which I'll abbreviate as SA. Sodium hydroxide is a strong base. How do we know that's a strong base? Well, there are 9 strong bases. These are the strong acids, the strong bases, and as I defined in a previous section, strong bases are the all the group 1 metals that have hydroxide, and then the bottom half of group 2 metals, so that have hydroxide. So that would include lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. And if francium were a thing, then we would include that, but we don't really have to, although that would be 6 there. But like I said, even cesium hydroxide is extremely rare. Rubidium hydroxide, for that matter, is kind of rare. But these are the 3 most common ones we use in our lab. We will never use those 2 down there, and certainly not francium hydroxide. Also, the bottom part of the heavy 2s, so we have strontium hydroxide, but because strontium is a +2 charge, we're going to have 2 hydroxides, so strontium hydroxide, barium hydroxide, and radium hydroxide. If any of these is in the reaction. We label that as a strong base, and sodium hydroxide is indeed in that, so that is a strong base. And when you have a strong acid react with a strong base and you have equal quantities of it, which is what we are proclaiming here in this equation, then it's going to completely neutralize each other. Acids and bases are exact opposites. They will neutralize each other. And so this is going to create a neutral substance. If we were to take the pH of this beaker in which these two quantities were added in equal measures, then we would get a pH of 7. Okay? So, if we were to take a look at another example of this, which is potassium nitrate and water. Now water is a binary compound, it has two parts that we just talked about, is hydrogen hydroxide. Alright, so hydrogen is the positive and hydroxide is the negative. Nitrite is the negative and potassium is the positive. We can go through a double displacement reaction for this, where potassium goes with hydroxide and hydrogen goes with the nitrite to create what we call nitrous acid. That was one of your practice problems from the acid section. Alright, so we want, this is the double displacement reaction showing the reaction of this thing taking place. What we want to do next is to describe which ones are the acids and bases and which one of those are strong or weak. So potassium hydroxide, well that was on that list of group 1 hydroxides, so we know that this is a strong base. Nitrous acid, HNO3 is a strong acid, but this is HNO2. HNO2 is not on that. Any acid that ends in OUS acid is never a strong acid, it's always a weak acid. Now, if we have a strong base, which means it's dumping all of its hydroxides in the solution when it dissolves, and a weak acid, which is only releasing some of its hydrogens in there, this is going to be the predominant determinant as to whether the solution that is containing these two is going to be acidic or basic. So we know that this is going to be a basic solution. So this is what you're going to be asked to do here. You're going to be asked to do double displacement reactions. You're going to be asked to identify the acids and base and which ones are strong, which ones are weak, and you're to identify which is basic. Now the one that we didn't talk about, well there's actually two that we've not talked about. One is if we had a strong acid and weak base, then this would have been acidic. The fourth option is a weak acid and weak base, but because we haven't really discussed and will not discuss in Chem 1 the way to measure the strength of a weak acid or weak base, we cannot come up with a great understanding as to whether the solution can be acidic or basic. So we'll worry about that in Chem 2. For right now, understand the relationship between strength and strong acids or strong bases. And again, if they're both strong, they're going to be neutral. If they're both weak, we can't do it right now. All right? So you have some practice problems to do. Have fun.